right, then let's get started. So, share the screen. So, welcome to this week's special edition of the Gardener Review meeting. We are talking about Kubernetes version 1.36 today. Toby and Ashish will present. The agenda is as usual. We look at the feature gates that have been promoted and were graduated, and about the security, removals and deprecations, and finally what was changing in Gardener. All right, then Ashish and Toby, please get started.
Yeah, thank you very much. I will get started. And I hope you can see my screen. And yeah, okay, so yeah, as Raphael already said, so today we will present what's mainly changing in Kubernetes 1.36 and what's exciting to look out for. The release was made in April, so it's a bit older already. So sorry for that it took a bit of time for this. But this release was titled Harde. So the entire release and release logo were designed in a Japanese theme. And the logo reimagines Hokusai's Red Fuji from 36 views of Mount Fuji, which fits the release version as well. The logo was designed by Natsuo Ide, and you can see some the Kubernetes helm drifting in the clouds, which is guarded by these two cats, which acts as komainu, which are usually found at Japanese shrines to protect it, and this should also represent the maintainers and all the different people from the six. Protecting Kubernetes in that way. Exactly. Without further ado, let's get started with the graduation ceremony. So I will be presenting the feature gates going to GA and beta, and then Ashish will go for what's in alpha, the security, deprecations and removals, and about what's changing in Gardener. So in GA, there might be some things that you already saw that we presented in 1.35 and 1.34 as well. So I will not go into 100% detail because most of this what is now GA and now beta has been already presented. So if you want a deeper dive, check out the other sessions, or there will always be also the cap linked. So if you want further detail, you can also check there. Okay, so the first feature that went GA is user namespace and pods. So this is a new spec. So in the pod spec, you can set host users to false, which is using Linux's user namespace feature to for example, mapping a privileged user ID or group ID in the pod to an unprivileged one on the host. So it increases the isolation or security. But by default, it's not used, so it's not mapped to a different user ID or group ID on the host. Exactly. Next up, we have a node log query getting into GA, which is a really nice feature because you can fetch, let's say, for example, the kubelet logs without needing to SSH onto the node itself. So you can query this endpoint, let's say the proxy logs, and then query for kubelet, and then you will get the kubelet logs for this particular node. But it's not only kubelet logs. There's also other system services that you can see. For example, you can do some pattern searching or query for different files, for example. This is a really nice feature. I think I didn't have it on my radar, but I think it's nice to have. Next up, we have the fine-grained kubelet API authorization. So back in the day, so to say, the health endpoint of the kubelet was on an unauthenticated read-only port, which was generally considered security worst practice, so to say, which is now disabled by default, and was moved to the authenticated port on the kubelet API. But of course, there on the authenticated port there was also an authorization scheme which was very coarse. So the logging agents, for example, needed proxy sub-resource access to query these health endpoint, but this would also give them exec. So they would also give them permission to go to call this exec endpoint, which could then execute any arbitrary code, for example. This was now made more fine-grained, so to say, and now there's configs, health, and the pods sub-resource, so you can control it more fine now, which agents or which resource should get what access on the kubelet API. Next up we have something that was, I think, very much talked about in greater detail, and I think is more prevalent than the other ones that we talked about now, which is the mutating admission policies, which are also luckily GA and then of course also enabled by default, which gives the opportunity to replace some custom webhooks with a Kubernetes native API or resources, so to say. So instead of deploying an own application into the cluster and registering as a webhook, you can now just skip that part and just apply manifests. Just as a general, so the policy consists of 3 parts before it gets active. So there's this mutating admission policy, this abstract logic. So for example, this policy sets a particular label to a particular value, so very, very generic and templated, so to say. And in it, you also specify the parameters, and then you can apply a parameter resource. So for example, a config map with some values or whatever, which then gives the whole policy set the owner label to something like, I don't know, companyexample.com on every pod, for example. And then there's this binding that we all know and love, that this binding concept in Kubernetes. So this links the policy with the parameter resource and packages everything up, and then the admission policy gets activated, so to say, or it gets done. So as I said, if you want to check out in further detail and examples, check the, I think it was 1.34 and 1.35 version of this meeting. Next up, we have volume source, or the OCI artifact or OCI images as volume sources going GA, which means that you now can mount OCI images or artifacts directly as a pod volume. So you can now specify just in the volumes image and then a reference and the pull policy, and then you can just use it as a normal volume like any other. So this means that you don't need to have an init container or sidecar to unpack the image, but Kubernetes directly takes care of it. Then we have the mutable CSI node allocatable property. So now CSI drivers can adjust the maximum number of attachable volumes at runtime. So it's now mutable. The problem was that the reported versus actual attachment capacity can drift or over time. So that, for example, the CSI driver wants to consume a slot that was not there. So the kube scheduler then makes mistakes, so to say, and then you get problems with volume attachments. Examples for this drift could be, for example, after the CSI driver starts, someone goes into the node and attaches something, or network interfaces get attached, GPUs or whatever. With this now being mutable, CSI drivers can detect this drift and then update the allocatable property. There's also a nice thing that is now GA, which is rather on the developer side, so to say, which will be handy for Gardener, is the declarative validation with validation gen. So instead of writing manual validation logic, we can now start using this validation gen tool released by Kubernetes, which takes these labels at API resources and then generates validation code based on those, which we can then wire up to be used by, for example, our admission controllers. We plan on leveraging this within our Gardener code base as well, in the places where it makes sense. But we haven't done it yet, so this is something you can maybe look forward to, even though from the user side there will probably no change really visible. Okay, next up we have stuff that went from alpha to beta in this version, and we start off by the kubec cap, so to say. So this was also already discussed in an earlier version, I think, of this meeting. And this basically gives users the opportunity to use preferences that are not bound to the kube config. So until now, there was also some customization possibilities within the kube config itself, but now it's decoupled in this preference kind that can be put into a file and then used by kubectl. And with that, you can do cool stuff like aliases for stuff that you use all of the time, for example, to let's say get a db prod, and then it basically writes out this alias, and then you can do some cool stuff or default some flags, for example, the server side to always be true by default. There's also in kubectl the kuberc subcommand now, which helps setting this up if you don't want to manually write YAML. Exactly. Then there's also the statusc and flagc for Kubernetes components. This is quite straightforward. So there's now these statusc and flagc endpoints on most of the Kubernetes components, which can be queried to get some information about these components. For example, on the left here, you can see, for example, uptime, Go version, the binary version, etc., and some paths. And for the flags endpoint, you can get the flags that this component was bootstrapped with. For example, the API server flags. You can see here the advertise address, for example. And with that, you don't need actual access to the Kubernetes API, or you don't need access to the control plane or SSA access. Exactly. Then there's a more, let's say, complicated topic is the constraint impersonation, which is now better, which gives, like the topic earlier, like the kubelet API, it's now finer grain control over who can impersonate who and what they can do. So, for example, you can now constrain a user to only impersonate generic users, or just impersonate service accounts, or any node, or just an associated node via the download API. So this is something that is quite narrow scope, but I think this is also quite nice to have, and hopefully we can see it in GASU. And oh yeah, very, very big topic. So there's now the relaxed validations for service name. So the service name validation switches from this validation to name is DNS label. And the effective change is that service names can now start with a number. This was earlier not possible, but now you can also call some, for example, your service one, some service, which is now allowed. This change is basically just to align it with other resource name validations, which also had the same name as DNS label validation. Exactly. Then there's also node declared features, which was formerly called node capabilities, which helps Kubernetes, for example, avoid scheduling mistakes or helps basically in clusters with version skew. So now nodes advertise which features they support via status declared features. And you can see, for example, something like extends WebSockets to kubelet. This was done when there was built WebSocket support, and this was basically changed from speedy. But if you have, for example, a cluster where some nodes already support these WebSockets, but some only support speedy, the API server can then see which of the nodes support this and can extend the WebSockets to the kubelet, for example. But not only that, there's also other features, for example, that then help the kube scheduler to make no mistakes by throwing a pod onto a node that, for example, has not this capability or this feature. Okay, and with that, I would hand off to Ashish and for the alpha features.
Thank you, Tobias. I hope my screen is visible.
Yes.
Okay, so I'll be covering the newly introduced alpha feature in the latest Kubernetes version, that is 1.36. So the first one is manifest-based admission controller config feature. So today's admission policies live in the etcd. That means so there is a window. So there is a small window at API server startup where there are no policies are enforced. So etcd might not be ready yet. And a privileged user can simply delete the policy which we are counting on. So for that solution, they have added a field, one-line field like static manifest directory. The API server reads every file in that directory at the startup. So before it serves any request, so it won't mark itself ready until all the files are loaded cleanly. So this is how the validation admission policy looks like, manifest based. So the name has to be ended with static.kts.io. So that suffix is reserved. So no one can create a REST-based object with the same name. So, and then the policy follows as usual. So manifest-based object uses reserved keyword which ending with static kts.ios. And so when the feature gate is enabled, creation of a REST-based admission object with the name ending with this suffix will be blocked. And objects are loaded from the disk and are not exposed via the REST API. So the kubectl delete command will not work for these cases. Moving on to the next, there were few features which were introduced as a part of DRA, that is dynamic resource allocations. The first one is list type attribute. So the DRA attributes are generally scalar. That means one value per attribute. But for certain type of topological relationship, scalar values are insufficient because a CPU can have adjacency to multiple PCI routes. So a CPU has a list of attributes. It's like suppose in this example, it has 2, and the GPU and NIC each have a single PCI route. So single one still works because a single element list is treated as a scalar value. And here you can see shows the resource claim block. it requests one CPU, one GPU, and one NIC. One NIC. And the constraint match attribute means that intersection of all the list among the 3 candidate devices must be non-empty. So in other words, like it must share at least one common PCI root. So here the intersection will be like 0, 1. So scheduler will pick that intersection. And for the backward compatibility, scalar values are treated as single element list. So the existing like device driver will work without any change. The next one is node allocatable resources. So when DRA manages CPU or memory, the scheduler has 2 separate accounting system like that don't talk to each other. So the same underlying physical resource is advertised and consumed by like 2 parallel processes. So one of the failure mechanism which the KEP has mentioned is scheduler level oversubscription, where the node resource fit plugin tracks the standard request and the dynamic resource plugin tracks the DRO allocation independently. So the scheduler is like completely blind to the fact that DRA draws from the same physical resource. So as a result of that, it places more pods than the node can physically support. So the fix for that is they have introduced a field. So a device can declare how they map to node allocatable resource using the node allocatable resource mappings field. And the node resource fit and dynamic resource plugins both will synchronize their accounting to the same ledger. And then the kubelet will incorporate the DRO allocation, and the pod status will record the actual allocation in the node allocatable resource claim status. So yeah, moving on. The next one is resource pool status. This is also part of DRA feature. So actually, there is right now there is no easy way to see how many devices are available. So resource slices store capacity data and resource claim, and resource claim tracks the consumption, but there is no like API level distinction between the available and the allocatable capacity. So the this KEP introduces a resource called resource pool status request. So you can create a resource pool request status request and specify the driver and the optional pool name, and the controller will fill in the status with like total device, allocatable devices, and the available devices, and you get the answer in a single API call. Moreover, it follows the same pattern as certificate signing request, means the controller processes each request exactly once, and it skips that and it skips the request that already have the status. And the requests are auto deleted after 1 hour if the condition type is completed, and up to like 24 hours if the condition type is pending. The next one is resource claim for workload. So the current limit of 256 entries in the resource claim status reserved for list means that a device can be shared by up to like 256 pods. This KEP targets a use case where a user wants to share a single resource claim among more than 256 pods. So for example, so as a fix, you can like attach resource claim field to the pod group and not to the each pod. So the controller will create one resource claim from the template for that group. So the pod claim uses the same name, like it uses the same name and refers to the same resource claim or the resource claim template. Here you can see in the example PG claim template. The controller then wires the reservation to the pod group and rather than each pod. So it bypasses the limit of 256 limit entirely. So the reserve for keyword references the pod group entirely entry instead of the potential of 100 of individual pod entries. And the resource claim is owned by pod group via owner references. So when the pod group is deleted, the claim is cleaned automatically. Now moving on to the gang scheduling, there has been also a few of the new features which was introduced as a part of gang scheduling. So the first one is topology aware. So the distributed workloads like require high bandwidth and low latency communication between the multiple pods to function efficiently. So the workloads like maybe it will be fragmented across different network domains, which can drastically degrade the performance and waste the like which are potentially very expensive hardwares. So a new field is introduced, which is called scheduling constraint on the pod group spec, where we can simply specify the node label, uh, node label under the topology. The algorithm operates in three phases. Placement generation will identify the candidate nodes, the subset where all pods can land. And then the feasibility checking will validate whether all the required pods can fit or not. And then followed by the scoring and selection, which will pick the highest scoring placement. The next one is workload aware preemption. So the tightly coupled workloads require ongoing communication between the multiple pods to make progress. So like disrupting a single pod will effectively disrupt the whole workload. So the core problem is like existing preemption mechanism does not address the need due to the pod centric like nature. So when a single pod of a coordinated workload is preempted, so even if the rest of the pods are still running, they are not actually able to make any progress. So the pod level preemption wastes the resources. The surviving pods are running, but they are doing nothing useful, just wasting the resources. So the disruption mode field on the pod group spec controls whether the pod in a group like preempted together. That is, you can mention all, which means the whole group is preempted as a unit, or independently, like the value single, which is the current behavior, like current pod by pod behavior. The priority class name and the priority field allows the priority to be set at a workload level rather than rather than to be duplicated on every pod. And the algorithm it sorts the potential victim groups by priority and attempts to reprieve the highest priority victims while keeping the placement feasible. The next one is job integration. So the job controller historically created created pods independently without workload aware scheduling constant. So with 1.36, gang scheduling was brought to the job controller, and that resolves this gap. So now there's there is a spec field. There is a scheduling field on the batch v1 job, uh, batch v1 jobs. Scheduling job. So like parallelism and completion mode, this is like a standard index job with 4 workers. And then there is a field called scheduling policy.gang, which will enable the gang scheduling. So like when the minimum count is not set, it will be defaulted to the parallelism, that is a value 4. And then there is a, so this means is key all the 4 pods must be scheduled at the same time or none are scheduled. And then the next field is topology.level. So topology field. So where all 4 pods must land in the same zone. The level, this level maps to the node level key used to identify the topology domain. And then the disruption mode, which was already explained in the earlier slide. So if pod in this job needs to be preempted, all the pods in the group are preempted together rather than one at a time. So this prevents like situation where remaining pods are running, but they are not doing anything. They're just for the resources and not doing anything important. So when the this scheduling field is omitted, the controller resolves to the basic scheduling instead of this one. The next one is sharded list and watch. So like controllers like kubestate metrics already implements horizontal sharding, but every replica still receives the full stream of events, like paying for the CPU and network cost, only to discard the items which does not belong to their shard. So this results in like wasted network and like wastage of CPU and memory on processing those irrelevant events as well. So the shard selector, like query parameter, this parameter moves the filtering up to the API server. So the replica 0 will get only pods whose UID hashes in the lower half, and the replica 1 will get the upper half. So for multiple ranges are also supported via the OR operator, and in order to like sharded kubestate across, like okay. So this is the use case of that one, which I said earlier. Okay. Now moving on to the native histograms and CRI listing. So as a part of this KEP 5808, they have introduced native histograms. So classical histograms has two problems. The first is like every histogram creates one time series per bucket. And the second is the buckets are fixed at compile time. So like if your data doesn't align with them, so you lose resolution. So like request taking 1 microseconds and one taking 4 milliseconds both fall into the same bucket. So the native histogram solves both. So like exponential bucket boundaries adjust automatically to the data. And both formats are exposed at the like same time. So client that risks for like that asks for the native gets it, or the client which asks for the current like classic bucket also gets the same. Like both are exposed right now. So with Prometheus 3.0, they are a stable feature and can be enabled per job with this particular field, scrape native histogram set to true. So and the next step is CRI list streaming. So like CRI list RPCs return all the results in a single unary response, and there is no way to break up all the large result set. So the NCAP has also documented two real GitHub issues where the gRPC limit exceeded at 11,000 containers or like 14,000 sandboxes, pod sandboxes. So when the limit of 16 MB limit is hit, the RPC fails completely and like and completely and not gracefully terminates. So new field stream container and stream pod sandbox RPCs send one item per message. Um, so yeah, the runtime then sends nil when done, and like kubelet aggregates into a single list, so existing callers are unaffected. So yeah, this is this one. Then moving on to the pod level resource manager. So like kubelet topology, CPU and memory managers operate per container and cannot use like pod resources as a basis of NUMA alignment. Like so, for higher performance workloads, minimizing the latency requires all pod resources on the same NUMA node. So they have two alignment model here. One is the pod scope, where the pod secures a single NUMA aligned pod for the whole pod, then partitions it, and guaranteed container gets the exclusive slices, and the rest shares the what remains. And in the container scope, per container preserves the existing per container alignment behavior. So in this example, the pod level budget is 4 CPU. So container one request 2 CPUs with the matching limit and make it guaranteed. So it gets exclusively 2 CPU allocation, but the container 2 has not requested anything. So it shares the remaining 2 CPU from the pool. So for this to be work, both pod level resource and pod level resource manager feature gate must be enabled, and only static CPU manager and static memory policies are supported. The next one is image volume digest. So image volume digest were not advertised in the pod status, unlike the container image digest. So it make it was making monitoring or GitHub operations like a bit difficult. Container images digest are already available in the container status. So why not do the same thing for image volume as well? So they have introduced a new field called image ref in the volume mount status. So image ref is the digest of the image used for this volume. It should have the value that is similar to the pod image ID. The field is optional and only populated for image volume sources. So other volume types leave it. It can leave it empty. So okay. So moving on to the ops and storage. So first one is like this is big, bit like a big feature gate like controller manager release leader election on exit. So like old behavior when the component loses its leader election, it shuts down shuts down and wait for kubelet to detect it as healthy and restarts it. So this can create like unnecessarily computational overhead and prevent graceful shutdown. The overall idea of this cap is to is that leader actively releases the leader release object when the context is cancelled instead of waiting for the TTL to expire. So in this diagram, you can see like before behavior. So like system arrives, the computation holds the component holds the lock until the TTL expires, and then the until the TTL expires, and then the standby is finally elected. But after system arrives, the component actively releases the lock, and the standby elected like can take over immediately. So it is a bit faster in this case. So the other gap is persistent volume claim unused unused since time. Like persistent volume can accumulate over time when the applications are deleted or migrated, their associated PVCs may be like left behind, consuming the storage resources and the incurring extra cost. So today there is no mechanism with the Kubernetes to determine like when a PVC was last actively used by any workload. So the reason this is done in Kubernetes is like they have the accurate knowledge of when a PVC is mounted by a pod and making it ideal place to track the users. So when a pod last referencing a PVC is deleted or reaches a terminal state, the condition is set to true. So this one will be set to true. And with the reason, no pod is using the PVC. So when the new pod will come and when the new pod starts and references the PVC, it flips back to the false state. So yeah, and the last transition time indicates that indicates like when the PVC was last changed between the used and unused state, providing the like equivalent of unused since time thing. So this was all from the alpha. Now moving to security deprecation and removals. So the first one is strict IP CIDR validation. This is on by default, meaning, and this is a breaking change for an existing API objects with non-strict IP CIDR values. So like QVP server will now reject all the four like following IP CIDR patterns. So the first one is IPv4 leading with zeros. So this has caused some security issues earlier also. So like libc based code will interpret octet with a leading zero as octal values, while the goes function ignores them. So like 012 can be interpreted as 12 in some system and 10 in another. So like now this will not be allowed. And the IPv4 IPv4 mapped IPv6 pattern. So this format exists for dual stack transition, but mostly causes confusion. So this will also be rejected now. The interface address CIDRs like where the host bits are set, meaning that this is not a network address, but different API can interpret this differently. So some can treat it as a host address, but other can subnet equivalent. So yeah, but the correct form is this one. And the next one is zone identifiers like these. So while valid in some context, but kept notes this might lead to some confusion. So yeah, this will also be like rejected. Next one is deprecating the service spec external IP field. So why this is deprecated? So CAP has stated one problem with that. Any user with the permission to create or modify service can claim arbitrary IP address, which is a security problem. So there is no built-in validation that can means Kubernetes cannot tell you whether this IP address is available or routable or authorized. And there are other better alternatives which exist nowadays, like load balancer, service gateway, IPs, and ingresses. So yeah, this is deprecated field. Then the next one is Git repo removal volume driver. So the goal is to remove tag vector for code execution through an ancient and unmaintained volume plugin. There was already an earlier security breach because of this, where it can gain a root access level. Driver can be exploited to gain root level remote code execution on any cluster nodes. So yeah, this one is logged and can no longer be enabled. This one. Okay, there were a few of the removed APIs. So like auto scaling v2 beta 1 and v2 beta 2, these were deprecated, and 1.36 has just now it has just removed it. So there were a few renaming of the fields between the two. So like min and max are renamed to min change and max change to eliminate confusion, and then the disabled is renamed to scaling disabled, and the resource is renamed to pod resources. Similar has been done for this one, scheduling v2, so v1 alpha 1, it is removed. So embedding pod groups within a workload spec creates a challenge around immutability, scaling, and lifecycle management. So pod groups was embedded inside a workload spec in earlier v1 alpha 1 version, but now it is a standalone component. The pod reference field changed from spec worker ref to scheduling ref, and the same goes with the field as well. So what has changed in the Gardener? As a core PR, feature gate, API groups, and admission plugins and controllers were updated, and the daemon set helper were synced with the upstream changes. New controller disabled for workerless suite, that is pod group protection and resource pool status requests. As a part of other PR Go dependency bump, the version KTS dependency was upgraded to 0.36 and the controller runtime was upgraded to 0.24. These will be covered in the later community meetings. And few of the removed API, which I already said earlier. And moreover, the kindset node is updated to 1.36, and the end test, which used by integration test, is also updated to 1.36. And there is still an open change, like OpenPR, where the end-to-end test will be running with Kubernetes 1.36. So with that, we wrap up. That is all from our side. So for more details about the KEPs, you can refer to the official documentations and changelog of Kubernetes. Yeah, that's all from our side. Thank you.
Thank you very much. So if there are any questions, you can also ask us directly or put them in the chat.
So we would have a couple of minutes left for questions. If there is anything, feel free. Apparently not. All right, then I guess we close the meeting. Thanks again for preparing this. And then we meet again next week for the regular meetings. Thanks for joining. Have a nice day. Bye-bye.
Thank you very much.
Thank you,
Bye-bye.
everyone.
Bye.
Thank you.
Bye-bye.
Bye-bye.
Danke.